Have you ever seen waves in water combine, sometimes making a bigger wave, and other times completely canceling each other out? This natural phenomenon, known as interference, is not just for water. It is a fundamental property of quantum particles too. Understanding how these tiny waves interact is key to unlocking the power of quantum computing. We harness quantum interference in qubits by precisely manipulating their wave-like properties to amplify the probability of obtaining the correct computational answer while simultaneously diminishing the probability of incorrect ones. This controlled manipulation allows quantum computers to explore many possibilities at once, a capability for beyond classical systems. The core mechanism behind harnessing interference lies in the qubit's ability to exist in a superposition of states. Imagine a qubit as not just a 0 or a 1, but as a combination of both at the same time, much like a spinning coin before it lands. Each possible state contributes a probability amplitude, which is a mathematical representation that includes both magnitude and phase, essentially describing its wave-like nature. When multiple qubits are in superposition and interact, their probability amplitudes constructively reinforce paths leading to the correct answer, and destructively interfere, effectively canceling out paths leading to incorrect answers. This careful engineering of probability amplitudes is what makes quantum interference a computational resource. To achieve this, we use a sequence of highly specialized quantum gates. First, gates like the Hadamard gate are used to put qubits into a superposition of states, creating the initial multitude of computational paths. Then, other quantum gates are applied to manipulate the relative phases of these superposed states. Think of phase as the position of a wave within its cycle. By shifting these phases, we can precisely control how different paths interfere with each other. These phase shifts are crucial because they dictate whether paths add up to increase the probability of a state or cancel each other out, reducing its probability upon measurement. A fascinating technique that truly highlights this is called phase kickback, which is central to many quantum algorithms. In algorithms like Deutschose or Grover's search, a specific type of quantum gate, often referred to as an oracle, is used to identify or mark the correct solutions. Rather than outputting a conventional 1 or 0, this oracle gate applies a conditional phase shift to the superposition state, effectively flipping the phase of the amplitudes corresponding to the correct answers. This subtle phase change is then kicked back to other qubits, altering their phases in a way that, when further gates are applied, causes the correct answers to constructively interfere, becoming overwhelmingly probable, while the incorrect answers destructively interfere. Ultimately, harnessing quantum interference is about orchestrating the wave-like nature of qubits. By carefully preparing superpositions, applying gates to introduce precise phase shifts, and then letting these quantum waves interact, we guide the system to amplify the desired outcome. This intricate dance of probabilities and phases is the secret ingredient, allowing quantum computers to tackle problems that are intractable for even the most powerful classical machines by efficiently filtering out the noise and converging on the solution.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.